Energy, the ability to do work. Then what is work? Well, work is a force exerted through a distance. Therefore, we can come up with the formula W for work equals force times the distance through which you push that force. The units for these are energy unit is the joule, symbolized capital J, force of course in newtons, and distance in meters. But wait, there's more. When you do work on a system, you change its total energy. Either, like imagine if you push something from rest, you would give it energy. If you pushed against something that was moving towards you, you would be taking away its energy. So you can remember that work is delta E, or the change in total energy. We'll come back to that. So how do you know how much energy a system has? Depends on what type of energy that you are talking about. We will focus in this lesson on only two types of energy. Kinetic energy, which is energy in motion, and the formula for kinetic energy, often abbreviated just K, but I'll be using KE most of the time, 1/2 mv squared, where m is the mass in kilograms and v is the velocity in meters per second. Remember, just the v is squared, not the mv completely. Gravitational potential energy is the other kind of energy we'll be going to dealing with, and that is stored energy, and that is m times g times h, which is the mass in kilograms, g, which is local gravity pull, and h, which is your height above whatever you've defined as your zero mark on Earth. Usually we would use the ground or the floor or whatever we're standing on. Make a quick little point here about unit equivalence. They both measure energy, so they should both kick out joules, which means that their input units should be the same. So the unit for mass is the kilogram, the unit for g is meters per second squared, and the unit for height is the meter. So we've got another meter there, so that becomes kilogram meters squared per second squared. And if we look over here, we can see that we do have an equivalent unit for kinetic energy. The 1/2 doesn't have a unit, but kilogram is the unit for mass. And then velocity is meter per second, and then we're going to square that, which is going to spit out kilogram meter squared per second squared again. So we can see that they do have unit equivalence. Also, we have power. Power is a way to think about power is that power is to energy as velocity is to distance. So it tells you, just like in velocity, you have velocity tells you the distance that you can traverse in a certain amount of time. Power tells you the work that you can do in a certain amount of time. So if you're very powerful, not only can you do a lot of work, but you can do it quickly. The unit for power is the joule per second, aka the what? Right. Oh wait, no, I misspelled that. The what? Oh wait, no, there's no question mark. Oh, sorry about that. The watt. The watt, capital W. So if you have like 7.5 joules per second, you'd say 7.5 watts. Just put an H in that, but there wasn't one. So here are some example problems that we could do. Just run through some of these real quick. Calculate the height that a 300 kilogram walrus must be above the ground to have the same potential energy as a 45 kilogram dog running at 15 meters per second. This is a little bit unclear. We're comparing the kinetic energy of the dog to the potential energy of the walrus. So let's calculate the potential energy of the walrus. It's going to be m times g times h. And we know that it's 300 kilograms. Problem doesn't say it's on Earth, so we'll assume that. Usually we'll assume Earth unless it says otherwise. Height is what we're trying to find there. The kinetic energy for the dog is what we're going to be setting that equal to, and that is 1/2. The mass of the dog is 45, and the velocity of the dog is 15. So we're going to set those two expressions equal to each other, and then we're going to solve that. So what I'm going to do is I'm going to get the h by itself by dividing out the 300 and by dividing out the 9.8. So do that to both sides of the equation. We'll have a height equal to 0.5 times 45 times 15 squared divided by 300 divided by 9.8. And that gives us an answer of a height of, let's see, I think 2 sig figs. I get 25.829, so I'm going to call that 26 meters. So a walrus, relatively small walrus, would need to be 26 meters above the ground to have the same amount of energy, potential energy, as that very, very, very fast running dog would have. There you go. Here's another one. We have a bison charging you at 22 meters per second, and you're going to exert a force of 250 newtons on him as he pushes against you. You're going to do that over a distance of 50 meters, and want to know what its final velocity is going to be. So we can see that we are basically doing work on the bison, so we're going to go back to the work equals force times distance formula. Although we can see here that isn't all we got to do, but it's going to be a start. So what are we going to do with that? Let's see. Well, we have a force of 250 newtons, and we're going to exert for 50 meters. So 250 times 50 is, of course, 12,500. So we have that much work that we're going to be doing on the bison. So we want to know what its new velocity is going to be. Well, its new velocity is going to do, well, we have to stop and think about this for just a second. We got the bison before. That's what a bison looks like, right? And we have the bison after. We're slowing it down. We're pushing, exerting a force on him, slowing him down. And so what we do know is what his total energy was before. His total energy before was 1/2 mv squared, which is going to be 1/2 times his mass, which is 505, times his velocity, which is 22, and then we're going to square that velocity. So now, if we plug those in, we can see that the total kinetic energy of the bison before we do anything to it is 122,210. Not worrying about sig figs for now. That is our kinetic energy of the bison before we do work on it. So, how much energy does it have after we do work on it? Well, we've just said that we did 12,500 newtons of work on him. So, that actually went against him. That's lowered his energy. So we need to subtract 12,500 from this number to find out what his total kinetic energy is after we've done that work on him. And that comes out to 109,710. That is his final kinetic energy. I don't know if I was very clear about this, but what we've been doing here is we've been using the work equals the change in energy. So we had the energy before was the 122,210, and then we're going to subtract off the final, or I guess, sorry about that. go back here just a second. The change is, of course, the final minus the initial. This guy only has kinetic that we're dealing with, so we're going to do final minus the initial. So 12,500 is equal to the final, which we're about to calculate, minus the initial, which was the 122,210. And so that is kind of showing you how our formula got us to where we're going here. This, of course, was a negative number because we were doing work on him to slow him down, not to speed him up. So there you go. So now if you add 122,210 to both sides, you get this number, which is his final kinetic energy. So we did all that, but that's not the answer because the question is asking for his final velocity, not his final kinetic energy. So we're going to set that answer equal to 1/2 of his mass times his velocity squared. So I'm running out of space here, so we're going to take 109,710. We're going to divide that by 1/2, and we're going to divide it by 505, and that gets v squared equal to 434.5, and then we're going to take the square root of that to get our final answer for the velocity of 20.8, which I'll round to 2. So we did all that work, and we went from 22 meters per second for the Bison to 21 meters per second. So we probably should have pushed harder. So that is that example. Oh, I remember I left myself more room. I knew this would take a bunch of room, but whatever. Finally, we'll do one last problem here. Calculate the energy that goes through a 60-watt light bulb if left on for 24 hours. Once finished, well, let's come back. We'll cross that road when we get to it. So 60 watts. So power is watts. It's work over time. So watts, 60 watts, that's a power. So we have 60 watts equals the energy or work over the time, but the time is 24 hours. And as you probably know, we can't use hours, so we're going to go 24 hours. 1 hour is 3,600 seconds. Get that into the metric base unit for time, and we got 86,400 is our time in seconds. So, I've got a minute and 57 seconds to finish this. We better go. So 86,400 times 60 is going to give me the work of 5184000. That's 5,184,000 joules, or 5.184 megajoules. So we've done that. Once finished, now calculate the mass of a boulder needed to be lifted 10 meters in order to have that amount of energy. Potential, gravitational potential, I think it's meaning there, because we're lifting a mass. So what we want to do is set that equal to the potential energy we want it to have. So 5184000 is going to equal to mgh. We're on Earth, and we're going to lift it 10 meters. So this isn't going to be very hard at all. So we got to take that answer and divide it by 9.8 and divide it by 10, and we can see that the mass of this boulder that we need to lift to make that much energy is 52898 kilograms. So 53,000 kilograms if we've done that all correctly. So that is about a 25-ish ton rock, and so you can see that leaving that light bulb on really actually does use up quite a bit of energy. Take a pretty big rock to make that much energy is what I'm saying, I guess.